with this button, and then we can start to have a presentation. Yes.
Yay!
Yeah. Good.
Amazing. Right, shall I start? Miracle technology. So my name is, can you all hear me okay?
Yes, we can hear you.
Good. Yeah, my name is Steve Webb from Webb Yates Engineers. We're a structural and mechanical engineering design practice based in central London and Birmingham, Bristol in the UK. We work all over the world, but mainly in London. Could everybody mute their microphones so that there's not a lot of people?
Okay, you're right. We'll do that.
So we try to encourage a lot of collaboration in our office between the different kinds of engineers, and we have some architects as well. We started our practice 15 years ago doing relatively small domestic refurbishments. I started my career as a tunneling engineer a long time ago, and I worked for Calatrava in Spain and other companies in London, so we worked on quite a big range of projects. So we still do little domestic jobs, but at the bigger end of the scale, we're doing quite big infrastructure projects. For example, this large underground baggage handling thing at Heathrow Airport is a £180 million project at Heathrow. But I'm here to talk about stone. We've been working with Amin and Pierre for probably 12 years on various stone projects. Stone is, I mean, I know that you have a big tradition of stone carving and stone masonry in Zimbabwe, and you have a lot of stone there. Stone is hugely abundant. I think we were working out that all of the world's buildings, if you piled them up in a heap at 20 square meters of 200 millimeter floor slab per person, would form a relatively modest 1,000-meter hill, really insignificant compared to the resources of stone that are available. Stone is typical stone, so this is a lump of granite, might have a strength of 200 newtons a millimeter squared. We work with granite, we work with limestone, we work with lots of different materials. The strength are always, even the weaker stones are about 100 newtons. We typically take that piece of stone, we crush it into gravel, we get an enormous amount of gas power, and we burn limestone to make cement. We batch it with fresh water and sand, sharp sand, which is bizarrely becoming scarce. We get a lot of reinforcement, formwork, we pour the concrete, we vibrate it, we let it set. At the end of all of that, 28 days later, we have a piece of concrete with a strength of 40 newtons. So my kind of contention is that, you know, really it would be much better just to use the stone in its raw state, far less energy intensive and far quicker, far less involved. So these are the strengths, the relative strength of stone divided by the carbon footprint in their production. So concrete uses a lot of gas, uses a lot of energy to be produced. Stone, you quite simply pull the stone out of the quarry and you start using it. Stone is stronger than concrete. The font sizes on this sheet are the relative strength divided by carbon footprint for those two materials, and you can see that stone is much, much better. We looked at, so we're quite often trying to compare the effectiveness in terms of carbon footprint of different kinds of materials. So this is a slide that shows a whole series of beams that can support a 1-ton car across a 2-meter gap. So on the top row, all of these are strong enough. So you have the softwood, 100 millimeters by 200 millimeters. They're all equal depth. Hardwood, engineered timber, narrower. Concrete, 28 millimeters, and steel, 2.1 millimeters. So these are not sections that you would necessarily use, but they're a pro rata rectangular section depth. On the row below are the stiffnesses. So the stiffness relationship is slightly different from the strength relationship. And on the bottom row are the carbon footprints for each of those beams. So this is comparing the effectiveness of the beam in achieving a particular goal and the carbon footprint involved in achieving it. So you can see concrete or the steel has about 22 kilograms of CO2 per meter, concrete about 14, post-tension stone, so that's a stone beam with a piece of post-tensioning rebar through it, has about 1.5 kilograms of CO2 per meter. So you can see that in comparison to steel and concrete, stone is really effective. So I'm just going to see if I can change that slide. So these are the relative physical properties, so you can see the difference in compressive strength. The other interesting thing about stone is that it has a very good tensile strength compared to concrete. So in the way that you would regularly have to reinforce concrete for shear and for bursting forces, actually, because stone is more effective in tension, you don't have to reinforce it so much. Then the stiffness. Stone doesn't suffer from shrinkage and creep in the way that concrete does. So one of the main drawbacks with concrete is obviously the long-term creep and the shrinkage effect of the concrete. Stones behave differently. Different kinds of stones behave differently, but by and large, stone doesn't suffer from that kind of problem. But on the other hand, stone is a natural material. So, and I think you know, engineers and you know, other practitioners, they prefer a homogenized material because they know how strong it is. So if you kind of whip everything up in the blender like concrete and then you let it set, then you have quite a consistent material achieving similar cube strengths all the time. Whereas with stone, you get quite, it's more of an unknown quantity. People don't know what to expect. So we take samples of the stone that we're going to use. We test all of those samples. We take 10 to 15 samples in flexure. We do a normal distribution of those. We take the best expected or lowest expected value based on 2 standard deviations. And we apply quite a high factor of safety. So we're reasonably, well, we're totally secure that the stone is going to be acceptable in its use with that level of redundancy. Actually, if there's a future for stone, I think it'll be in better assessment of strength, non-destructive assessment of strength. So this piece of limestone here failed at something like 60% of the expected value because of the ammonite. The ammonite is in the worst possible direction for reducing the strength of the section, and it's completely invisible from the outside. So you need to account for all of those variations. We started designing stone. Well, in actual fact, yeah, this is a cantilever stone, or what we would describe as a cantilever stone stair. It doesn't actually cantilever. The tread above pushes down. The tread below supports it. The tread in between is prevented from rotating out of the way by its fixity to the wall. So we're converting what is a cantilever moment, normal to the wall, into an in-plane torsion of the wall connection, which means that you can get stone stairs to stick out of walls in that way. So we started designing staircases like this with timber. So this is a staircase that I made myself, which is why the workmanship is so terrible. But this is a whole series of plywood boxes screwed onto a 50mm terracotta wall in it's my flat in Spain. 6 wood screws, wall plugs, bit of glue smeared over the paintwork. This wall is 50mm thick, hollow terracotta tiles. There's absolutely no way that this is cantilevering. So this is a kind of demonstration of that principle. So we started doing lots of staircases like this. So the one on the left is a solid oak one, and the one on the right is a plywood one. Pierre, the stonemason, came to us and said, well, if you can design these stone staircases in timber, then maybe you can design them in stone. So we started to design what we would call, in inverted commas, traditional stone cantilever staircases. This is a modern version where we've cut away some of the low stress stone, and this is a project with Amin Groupwork. So this is quite a non-traditional stair. There's a rough cut finish to the underside, but the principle of each tread being built into the wall and working in that way is the same. The cables in this instance are just for containment of the balustrade. They're not there to support the stone treads, and in actual fact, the cables take support from the stone rather than vice versa. But Pierre, the stonemason that we were working with for so many years, could only sell staircases, or his company could only sell staircases to people who have a stair flight and an adjacent wall. So it's kind of limiting in terms of who you can sell stairs to. So he was very keen to develop a free spanning stone solution. So we started looking into reinforcing the stone, and we're certainly not the first people to do this, although it's still quite rare. So this was an early test. It's a 3.2 meter span. They're 50 millimeter thick, essentially flagstones or paving slabs. There are two 8 millimeter cables with 5 tons in each cable, and the cables assume a parabolic trajectory so that the sag in the cables resists the dead weight of the stone, and the tension in the cables pushes the ends of the stone together. So with this, we were able to make this bench. It spans 3.2 meters under a full domestic load, 50 millimeters thick. So to get the equivalent behavior out of concrete, you probably need 100 millimeters. So it's a very nice demonstration of just how thin and effective reinforced stone can be. We gradually started making small reinforced stone straight flights, and then helical flights, and got more and more ambitious. This is a staircase in the north of England. It's got a 270-degree helix. It's got two 12 millimeter cables through it with 12 tons in each cable. This is a test with Pierre and Paul at the Stonemasonry Company. The tensioning order was very important. This test failed because the application of the tension wasn't in the right order. And it failed quite dramatically, but we learned a lot from that. And I think because these things, there's no codification for this form of construction, so you really have to kind of learn on the job, which I think is interesting and also a little bit intimidating sometimes. This was a successful test of that stair at 75%, and this is a finished stair. So we've done now, I would guess, 30 or 40 staircases of this kind. That stair measures 1.4 meters. Each tread is solid stone. There are two 12 millimeter cables running through there. There are two flights, 270 degrees. So really that's quite a thing. And you know, we're getting paid reasonable fees to design things like this because they're for rich people's houses. But actually you can see from this demonstration that making simple columns and beams would be very easy, you know, by comparison. Then we were designing some staircases that were, well, in this instance, it was going to be a steel stair clad in travertine marble. And we were thinking, well, we can post-tension the stone, make it solid travertine, post-tension it. But then we were thinking, actually, what's really interesting is not reinforcing it. So there's a whole wealth of Gothic architecture where people are building massive structures without any reinforcement, very pure, very simple. 1,000 years ago, I think we would really struggle to design some of those buildings today. But so this polystyrene model is the way that we were trying to work out whether this staircase would balance. So there are lots of different components in the stair that interact in different ways. It's quite difficult to analyze with a computer. If we can make it stand up in polystyrene, then we can definitely make it stand up in stone. So we were able to make this thing stand up. If anybody, because it's so light, if anyone breathed or sneezed or coughed near it, the whole thing collapsed. But actually, it will stand there for a few seconds. So what we're so what we're doing here is forming an arch on one side, a traditional stone cantilever stair supported by the arch, and then torsionally interlocked segments on the landing. It's hollowed out to make it a little bit lighter, and that's the finished stair. So there's a balustrade, and all these stairs, we take the photos before the balustrades are fitted, so you can see more clearly what the structure is. This is by Atelier Romeo, Italian stonemasons, and Jamie Faubert, architect in London. But yeah, this is totally unreinforced. No steel, no cables, no tricks, just stone. it's on the 5th floor of a very old concrete building. We needed to support the weight of it. Initially the idea was to have a whole series of very heavy I-beams to support the weight of it and actually step up when you got to the bottom of the stair onto a platform. But we were thinking it was a bit of a shame to have that interruption. So this plate is 50mm steel waffle plate. It's fabricated to curve upwards, and then it's jacked flat. And then when the staircase is built on it, the weight of the stair equalizes the upward curvature, so that all of the dead load is carried to the supporting walls on the left and the right, and none of the dead load goes into the slab underneath. So it's kind of a good way of holding the stair up. This is a sculpture by Anthony Gormley. So this is kind of figurative representation of him. This is his, I don't know whether you can see my mouse, his head is the big block on the top right. His hand is under his head, his forearm, his leg, ankle and foot on the floor in front of him and on the left. He wanted this to last for 200 years, to be rebuildable, and so quite difficult to bolt it together. We couldn't see any fixings and connections. So that's Anthony Gormley. So we were looking to see if we ordered the fabrication in a certain way, or we ordered the erection in a certain way, then we can make these stones lock themselves together. So the one thing is they need to stand up under their own self-weight, and the second thing is if a bunch of drunk rugby players climb up the back of here and try and push that off, they can't do it. So we actually very slightly changed the order of the blocks from his original design. So you can see this block here catches the back of that one. So this one, which carries the load from here, is in balance with this one. The head on top. There are a whole series of tenons and in fact kind of Lego studs that sat on top of the stone. So the stone, if you put one stone on top of another with a flat surface, obviously it rocks because the surface is never completely flat, and as a consequence you don't really know where it's bearing. If you put 3 Lego studs, you know exactly where it's bearing because it can only sit on the 3 points. So all of those connections are made with these studs. Occasionally there are projecting tenons that are brought together by a subsequent stone. And then this project is Amin's building in Clerkenwell that he's no doubt going to talk about in more detail in a moment. We developed a lot of know-how with stone because we're designing rich people's staircases, but actually our idea is that quite a good thing from a sustainability point of view and just from a point of view of pure logic, to reintroduce stone as a structural building material. So we had the opportunity with Amin to design this building. It's a concrete frame on the inside. So you can see this is our Revit model. You can see the core, stability core, concrete stability core, 2 75mm thick flat slabs. That's the only concrete structure, no columns. So all of this brown stuff is the stone, load-bearing stone supporting the concrete slabs. So here you can see, because you don't want to have a concrete contractor coming to site and then building a little bit, and then a stone contractor coming and building a little bit and going away again, and then the concrete guy coming back and them all blaming each other for delays and whatever interruptions on site, we thought it was a better idea to build the whole concrete frame first and then to build the stone afterwards. So the whole concrete frame is built on these yellow props, temporary formwork, and then the stones are lifted in single pieces, then the temporary props are removed. So that's the finished thing. It's really, people are very surprised and really pleased that it's a load-bearing stone building. I mean, they're load-bearing stone columns. It's been going on for thousands of years. I think it's somewhat surprising that people are so amazed by it. We were thinking, what can we do with stone in other parts of the building? So if you make a stone vault, it's obviously got a lot of curvature. It's not very convenient for a lot of building types. How can we make a flat vault? So this is, these are 40mm Portuguese limestone, 500mm square tiles. So rather like a plastic tile puzzle where you make the face of Mickey Mouse or whatever, the plastic tile puzzle doesn't have any rails in it. The tiles don't fall out because they're interlocked torsionally. So here, this is supported on the edges it spans 3 meters in both directions. There are no cables or reinforcement. The corners are clamped together so they can't move up and down next to each other, but that's the only connection between the stones. There's no moment connection between the stones. Basically what happens is one piece of stone is supported on 3 corners, making the 4th corner stable. The next piece of cut stone is supported on the 2 edge corners and the corner of the first bit of stone. The one after that, the same. So subsequently, you can build the whole thing out like that in maybe an hour and a half or 2 hours. We built this thing. So it's spanning 3 meters, 40 millimeter thick tiles, no reinforcement, tiny carbon footprint, completely stiff, quite redundant. So if you break a stone, actually there are lots of other ways for the forces to travel around, so it doesn't collapse. So we're thinking this is a really good way of building unreinforced, reusable floors in buildings. So this is kind of postulation for what a building system of that kind might be, bringing together the various things that we've kind of learned with staircases and Amin's building and other stuff. So you might have standard beam components that are post tension together, standard column components and floor plates, build columns and beams and floors. There's hardly any reinforcement in this, very low carbon, it's demountable and rebuildable. So this was a kind of prototype, not a very pretty prototype, I have to say, of that kind of construction. So you can see the beam, the end of the post-tension rod columns, and the floor plates built in to there. And there's me jumping up and down on the end of it. And that's the end of my talk. Thank you very much for listening.
Steve, all I was going to do is speak over some of those slides because not a separate presentation, unless Zizi or Dr. Banda can press share screen, enable multiple users. I'm going to have to talk over your slides. So if you scroll back to
Oh, I just gave a, do you want to request control, I mean, and you can scroll through, or do you want me to do it for you?
Yeah, okay, fine. How do I do that?
Top view options.
Sorry, where's that?
The very top of the screen,
options,
it says view options, and it says request remote control.
Gotcha. Request. I've requested it. Have I got it now? Can you, how's that gone, Steve?
It's not me who's giving you permission.
Oh, I see, right.
It's,
okay. It's easy.
Dr. Banda's.
Yeah, Dr. Banda. Okay. Aha, I think I've got control. There you go. Where was your Caroline Place before or after this?
About a quarter of the way through before.
Before this, yeah, sorry. After this?
Yeah, before that. Keep going.
So before. Blimey. After that?
Yeah. It's an epic.
It is an epic, isn't it? Yeah. Sorry. So everyone's still here.
Are you going the wrong way? You're going the wrong way.
Oh, I thought you said after. Okay.
Well.
Okay. All right.
After and.
Yeah. Yes, exactly. Thank you very much. Very useful. I don't think so, Steve. I think it's.
No, it definitely is because it's
It's before all this. Oh yeah, there we go. Yeah. Is this the only slide you have of it?
Yeah.
Okay. Now, okay. I mean, the only thing I'll add about this is that if I can annotate, This staircase is essentially, as Steve described, bolted into, fixed into the wall, and then obviously one tread is resting on the other. Now, normally with these sort of staircases, you'll end up with about 40% of stone wastage. What we asked the stonemason to do is essentially take one block and cut it into two treads, so it minimizes the wastage. Slightly complex to do if the staircase, I mean, it's much easier to do when you get a straight run, but slightly complex once it becomes a spiral or a helix. But what they did is, you can see there on the underside of the stair are the drill marks of the splitting. So they had to drill them at an angle, at a continually curving, if you like, angle, to manage that. But what we learned was, one, you minimize wastage, so the staircase is ultimately cheaper. And as Steve has described, it's done in a single material. There's nothing particularly complex about it. It's fairly inexpensive, and you get, this is in travertine, you get a fairly beautiful result at the end of it, including where you would like to retain perhaps the actual extraction of the stone itself. In this form, the drill marks, the stone extraction from the quarry, and stonemasons working. Okay, so if I try and mouse go on to the next slides. When we came to actually undertake a building itself, which is obviously an unknown, it's a challenge that the UK or in England no one's undertaken for about 100 years. So the knowledge wasn't really there at all. And when we talked to our design team, obviously Steve is up for the challenge and imaginative with the challenge, and Pierre, who might join us later as a stonemason, working on those staircases as a French stonemason. Now, the difference between French stonemasons and the rest of Europe is that they have, I guess, an unbroken chain of education for about 1,000 years of working with structural stone, while in the UK, all our stonemasons are trained in decoration alone. They haven't any idea about how to use stone structurally. So we asked Steve and Pierre if it was possible to use stone for structural purposes on a building. And the answer from Pierre was, well, actually in France, after the Second World War, it was called austerity construction, because it was far cheaper to extract stone and build housing up to 8 stories tall, ground plus 8 floors, in stone than it was in steel or concrete. We asked, well, what happened? Why was it stopped? Well, because after the Second World War, politically, steel and concrete was emblematic of the modern period, the modern age, modernism, if you like, and stone was emblematic of the past. So several generations that had brought Europe to war. And politically, everybody was much more keen on the idea that all new housing, the rebuilding of Europe, should be fully modern in its appearance. So despite the cost, steel and concrete took dominance, and stone skills began to diminish. Now in France, those skills are still there. So we set the task to our French stonemason to work with Steve and educate essentially some UK consultants. And what we quickly found out was that the UK consultants, the cost consultants, the project managers, were under the impression stone would be highly expensive and complex, take a long time. Surely stone must be expensive. No one's worked in it purely because it must be expensive. And it's very easy, obviously, to test that. We asked Pierre, how are you going to give us a cost? He asked Steve, simply calculate the volume of stone that's required for each column and each beam, add that together as a full cubic meter volume, give it to me, and I will give you a cost for extracting the stone from the quarry, transporting it and erecting it on site. That cost was a fraction of the equivalent steel or concrete frame structure with all its layers that we require in the UK. So those layers are for fireproofing, waterproofing, and thermal separation. So all those extra layers obviously add complexity to the construction, not just in the material, but also the different trades. So the different men that have to come on site and do each one of those. If you remove all those and just have a stone column that performs all of them in one go, i.e. you lift it into place, that's it. No more other layers. The cost of the superstructure suddenly reduces. So that was a surprise to everyone. The cost consultants, the project managers, and obviously us as architects as well. And the question was raised, well, why don't we use it? And of course, I've given you part of that reason is because in the post-war period, we wanted to be emblematic of modernism, and everything should be in the modern materials, as it were. So here you can see that you know, slowly we're learning year by year more and more lessons. Here you can see we opted for a concrete slab, and if you look carefully, at the edge of that concrete slab are cast in metal receivers. Yeah, so the stone columns go up while the slabs are sitting on temporary props. Behind those stone columns are metal bosses that are wedged between the columns and beams, and then they're simply bolted to those metal receivers of the floor plate, and then you remove the temporary propping. So there's your superstructure going up, and that's all automatically already fire rated, weathered and thermally broken, separated from the envelope. Hence the speed in construction and the reduction in other materials and trades that come on site. What we've learned since then is that instead of a concrete floor slab, what would have been far quicker would have been a timber floor slab. So here, slowly but surely, the construction method of cross-laminated timber is taking hold. Now, 10, 15 years ago, it was quite specialized, but it's becoming more and more common now. Then you have a decision. Well, how do you finish that stone? You know, you can take a number of architectural finishes to it, and traditionally it's called dressing the stone. So all the way up to 100 years ago, so call it the last 1,000 years in the UK, that stone would have been dressed in the Norman style, but ultimately still its superstructure, and that continued all the way through the medieval period, the Renaissance and neoclassical period, the Gothic revival period. All those buildings you see in the UK are still superstructure, so the structural engineering integrated with the architecture, and it's just dressing. Here the decision was made once we saw the stone coming out of the quarry, that stone has actually got its natural sedimentary layer with ammonite shells, fossils, quartz pockets, and fossilized coral quite visible. We decided, well, why not leave that inherent beauty in the stone evident on the facade and leave it relatively untouched, which again obviously brings down the cost of, because you're not bringing in extra cutting and carving. So the lessons I think we'd like everybody to take away are that if you extract stone from a quarry, transport it and install it, drop it on site as the superstructure, it's a fraction of the cost of casting a concrete frame or a steel frame, erecting a steel frame, and then cladding it. Additionally, what we found, and again, some of these lessons you learn as you're in that process, because no one's done it in this country for 100 years, some of the other lessons you learn are on sustainability, and as Steve has explained, here, our sustainability engineer informed us that we'd saved 92% of the carbon footprint of the building had we done it in steel and then clad it with all those extra layers. And initially, we couldn't understand why, and then eventually it dawned on us, of course, because stone has no carbon footprint. It's just sitting in the ground. It was made, in this case, sedimentary limestone. It was made 250 million years ago. The carbon that you're burning, you're expending, is in the cutting and transportation and erection on site. And had we managed to find a UK quarry to supply the stone instead of a French one, we would have saved 95% of the footprint. But because we have to transport it across the channel, it was an extra 3%. What we've learned since is that if you combine the structure, instead of using any concrete at all, if you combine the structure with cross-laminated timber, then your and stone superstructure exoskeleton, then your building is actually carbon negative, because obviously timber is a carbon absorbing material as the trees are growing, as it were. So you end up with a carbon negative building. That's the equivalent of had you built another one next door to it in concrete. I think I'd like to leave it there because Steve's pretty much covered most of your structural aspects. So I've sort of reiterated those, why stone wasn't used in Europe until more recently. And we're hoping that people will take it on, not just for cost purposes, but also for sustainability purposes.